Okay, with energy defined, the next thing that we can do is we can put it in terms of the Fourier expression for our function. So what's going to go on here in this set of notes, or these few lines of notes, expands on just a couple of lines that appear in Schabenberger and Gotway on page 63. So we begin with our definition of energy here on the left-hand side. And then what we've done here is replaced F with its Fourier representation. So you can think of it as, this is the basis, that countable basis of sines and cosines, which completely recovers our original function. So what we have here is this quantity in the parentheses squared, and we've got this sum of terms, and so one would think, of course, that one's going to have a lot of cross terms, but we actually don't, because if you remember, this is a nice basis. The sines and cosines are orthogonal, and so the only thing that's going to not be zero when all of those cross terms are going to be zero. Our cosine squared terms are going to be p. Our sine squared terms are going to be p. And so this next line has all of those cross terms zeroed out because of the orthogonality. And then here we've got a p, and here we've got a p, which gives us this expression here, which you'll see in Schabenberger and Gotway. So just using our properties of orthogonality, we can get from this expression of the energy to this expression, which I have circled down here, of the energy, which is in terms of the squares of the coefficients a0, an, and bn. This relationship of the energy to the coefficients of the Fourier series is known as Parseval's relation. And so what we can do is when talking about the energy, we don't need to talk about the ANs and BNs separately. We can basically combine them, and so we can define C0 to be A0 over 2, and Cn to be this expression of AN squared plus BN squared, and this expression which we had in terms of the ANs and BNs can be written very simply as this expression in terms of the CNs. There is also this notion of power. So the total energy has P in it, the length of the period. Well, 2P is the length of the period. And so the power then is just the summation of the CN squareds. Okay, so what we've done here is we've got this number called energy, which tells us something about the amount of activity of this periodic function, and we can get that amount either by actually integrating this function, or it comes kind of more cleanly through the Fourier representation of the function. And what this allows us to do is we can, one thing people do is they look at the so-called power spectrum. So what we can do is we can look at Ci squared in terms of each of the frequencies. So if each n corresponds to a frequency of the sine waves, and we can break down this total energy in terms of the individual contributions of each frequency to the energy. And the power spectrum, the sum of these, of course, is the total energy. So I have this note which just says that we're looking at the CNs rather than the individual ANs and BNs, which could be positive and negative, and of course the ANs and the BNs are tied to a specific frequency, which arises from the argument of the cosine and sine function. But when we're just looking at total energy, we don't need to look at the ANs and the BNs individually. Okay, so we're going to switch our thinking now, and we're going to jump from periodic functions and Fourier series to non-periodic functions and Fourier transforms. So we're still dealing with deterministic functions. We haven't, when we're done with this section, we won't be completely where we want to be, because we'll eventually want to be doing Fourier transforms of something that's random. But we're not going to restrict ourselves to periodic functions. Okay, so this quote from Schabenberger and Gotway says, we are still interested in the energy and the power distribution of a function, but the power spectrum will no longer be discrete, and as there will be power at all frequencies. And the transformation is not going to be able to be written in terms of coefficients, or I should say the function after transformation is not going to be able to be represented by a countable collection of coefficients. Okay, Schabenberger, please read this section again, because I think Schabenberger and Gotway and these notes are going to complement each other well. They're going to make an analogy between Fourier analysis of periodic and non-periodic functions and discrete and continuous random variables. So the expressions that come from a Fourier series representation only exist at these discrete frequencies, right? We can either talk about the CNs or we can talk about the ANs and BNs, which cover the function. But there is no value of these coefficients in between these frequencies, because of course, as we said, if we have a periodic function, only certain frequencies will contribute. We're going to have this same notion of power spectrum, but we'll think of it more in terms of like we think of a probability density, where if we want a meaningful value, we'll have to perform an integral over some range of that density. Okay, so put that in the back of your mind. We'll circle back to that. So we begin by saying, suppose we start with a non-periodic deterministic function, and to do a Fourier transform, we need the function to be integrable. And so for Schabenberger and Gotway are going to say that imagine that the function goes to 0 as s goes to infinity or negative infinity, and furthermore that the absolute value of the function is the integral of the absolute value of the function is finite, so the function is integrable. Given those two, given those conditions, then we can recode g of s as this capital G of omega, and omega is we're going to think of this as the frequency. So Schabenberger and Gotway are again going to talk about the inverse transform and the transform all together. The second line is the transform, where we begin with the function gs. We perform some transformation of it, so we integrate out the s while introducing this new variable omega, and we get a new function g omega. So we're going to integrate g of s with e to the negative I omega s, and of course that I is our usual imaginary, denotes an imaginary piece to our number. So we're dealing with complex numbers. And then we can recover the original function by performing the inverse transform. And so we take our capital G omega, integrate that with respect to e to the positive I omega s, and we will recover exactly the original function. And so this agrees with our notion, our usual notion of transform, in that we're starting with a function, we're recoding it as another function. This other function has all of the information in it, and in fact we can go from this recoded function back to the original function. Now, Fourier when you hear the word Fourier, you should think frequencies. And and we said that, we're interested in power distribution and stuff. So where are the frequencies here? And it may be obvious to you, but you may have forgotten. But the frequencies, the sines and cosine waves, are inherent in this definition because e to the I omega s is equal to cosine of omega s minus I sine omega s. So this is a complex number. You can see that we're going to get a complex number where we've got a real part, which is the cosine, with frequency w, and the imaginary part is sine with frequency w. If you're confused about how this arises, if you think about the Taylor representations of e and cosine and sine, it becomes pretty clear immediately how these two expressions are equivalent. Okay, so returning to our definition of transform, we said we're going to transform our original function gs by integrating with respect to e to the negative I omega s ds, and we can write the exponential expression in terms of sines and cosines, which is what I've done here. And so I said omega was the frequency, which is not quite correct. Omega is such that 2 pi times the frequency is omega. But we can we can write this expression in terms of the frequency f. I guess I should have a 2 pi f here instead of an omega. So this looks similar. If you pause for just a second, we're integrating these things, so we don't have a sum of cosine pieces and a sum of sine pieces at different frequencies. Instead, we're really integrating over all possible frequencies. And unlike in the previous Fourier series expression, we're going to have real and imaginary parts, but the real parts are going to serve as the ANs, sort of the coefficients, if what you will, in this continuous setting, and the imaginary parts, the BNs, were the coefficients associated with the sine part. So the imaginary parts are related to the sine waves. If we think of assembling our original function g from its sine and cosine pieces, these no longer only exist at discrete frequencies, and so we have to integrate the transformed function g over all possible frequencies. We can't add them up because it's not discrete. We've got to integrate over all, the uncountable number of frequencies that we're now considering to recover our original function, little g. So that relationship that we saw earlier about the power spectrum still holds. We can see that this is a measure which is sort of equivalent to energy. Before, we had energy defined in terms of one period of the function. Now we've got to talk about the total energy in the whole function, because of course we can't restrict to an interval because the intervals don't have repeated information like they do in a periodic function. But if we think of this as energy, it turns out that that information is contained in the squares of our, the integral of the square of our transformed function g. And if you look back to what we called Parseval's relationship, which was talking about the cn squareds, this thing on the right-hand side is playing the role of the Cn squareds. And this relationship is known as Plancherel's theorem. So, as I said earlier, our transform function, capital G omega, contains all of the power information in G of S, and that's not surprisingly because, well, it contains all of any information about our original function, lowercase g. So we can think of plotting this. I mean, we can talk about this as a function of w. We're going to have some g of w. And then if we want to talk about the power of around some frequency, basic, or some interval of frequencies, we would integrate to get that total number. This is just breaking that down into an infinitesimal. The absolute value of GW squared, you may be thinking, hey, why do I need that absolute value? And of course we need that because we're talking about a complex number. So to get this, we would take the complex number times its complex conjugate. But you know, if this becomes really small, this becomes a dW. We're talking about the energy reflected it at a particular frequency. So, getting back to this analogy that Schabenberger and Gotway wanted to say, you know, we said they wanted to make an analogy between Fourier analysis of periodic and non-periodic functions to discrete and continuous random variables. When we've got a continuous random variable, we can describe it through a density, and the meaningful quantity, the probabilities, arise from integration, and that interpretation carries over that this g omega, to get something meaningful, we have to integrate it to get an energy number. If our function is real valued and even, this is critical. If it's even, then the sine term is going to drop out. So again, think of, you know, some even function. So I don't know, something like this. It would have to look the same way going in the other direction. There can't be any sine contribution to this because sine is an odd function, and so if we have the sine wave poorly drawn here, we can't have any contribution to this at all. And so from a wave that looks like this at all. So only the cosine pieces are going to carry over into the transform, meaning that there's not going to be, if this is 0, we're only going to have the cosine pieces. And why do we care? Why do we mention this? Well, looking forward, what we're going to do is we're going to perform a transformation, a Fourier transform, on a covariance function. So we're looking forward into doing this for something random. How do I talk about a random field? The tool that we are becoming familiar with is we're going to characterize a random field largely through its covariance function. If I want to do a Fourier transform of this random field, a function we have to describe that is the covariance function. This is not dissimilar to looking at a characteristic function where basically we start with a random variable, we think of a function which characterizes that random variable, namely its density, and we perform a transformation of its density. Well, we don't have a density to write down for a random field necessarily, but we can write down its covariance function. And so that's where we're going to make the jump from deterministic functions to doing transforms of random processes. So I'm going to cut off this video here so that they're in digestible chunks. There will be a part 3 for September 11th's lecture to be recorded and posted soon.